Okay, we're going to take these last two problems, and this is really the two that put it all together. This one is the one that puts it all together and what normally we get as a single problem, but we want to make sure you kind of get the hang of this. Let's take our box again. Here's our box on this ramp. This is 20 degrees. 20 degree and a 20 kilogram box on there. Make sure you got that right, 20 degrees, yes. The box has a weight. 20 times 9.8 is going to become 196 newtons. So that weight is a vector of how much it would be to lift that up. But the board, this ramp, only has to carry part of that. That part of it that's in the, it looks like it's in the x direction. We call this force perpendicular. Force perpendicular is related to the weight times the cosine of theta. Okay, normally we think up and down is y, but on ramps we flip that. So this ends up becoming 184, I believe. Yep, 184 newtons. Okay, so not all of it's any longer sitting on the board because some of it's going down the board. That means the normal force, which comes perpendicularly off, and that's a horrible horizontal. Sorry. It'll come out like this. It's probably more like that. Normal force here equals 184. Now that's important. The normal force helps me to understand how much the board is pushing back will determine what kind of frictional force that's here. Okay, the force of friction comes from whatever the normal is times this coefficient. If that were 0.1, it means that it's 10 times easier to pull it than it is to lift it. That's a little less than 0.1, so we're going to just calculate this over here. So the force of friction is equal to the weight times the 0.08. Sorry, not weight, normal. This is equal to the normal force times 0.08. When I take 184 times 0.08, I get 14.7 newtons. That's how much friction is going to go against this box sliding down. Okay, so we're going to put a little equal sign here, and that's going to be 14.7 newtons. Until this has got enough force, 14.7 newtons at least, down in this direction, it will not slide. So what is the last piece of this puzzle? Is I have to figure out what this force is, and we call that force. It's parallel to the slope, so that's the one way I remember this. Force parallel, and it is related by saying the weight times, we normally think of this as x. I'm going to flip that. Instead of being cosine with x, I'm going to say sine of theta. Okay, I'm going to have to move that value up here. If I take the weight, 196, times that sine of theta, then what I'm going to get is a 6.7 Newton force. Will this box slide down this hill? 6.7 newtons is what's going to be, its weight is encouraging it down the hill by 6.7. This says I need 14.7 newtons to make that box slide. Is the box stuck or will it slide? It is stuck. Okay, we'd still have to go a little higher before this would start to slide. So that was a toughie. That's the culmination of all we've done. There's always those four forces here. You've got weight, which is straight down. You want to know what the perpendicular part and the parallel parts are. Perpendicular feeds us what the normal force is, and the normal force helps us figure out how much friction there is. And the parallel force then is what's in competition with the friction to solve if that's going to slide or not. Good job.